word sizes. Yeah.
So are you trying to turn them to console, or are you doing like ASCII?
No. You're able to draw pixels, and you got 8-bit colors.
Alright, guys. So a few things to clarify first, because this can be a little bit confusing. So you have seen all the pictures like something like this, or it labels a Fox layer at a different location. So this can be really confusing. So see here in this picture, the Fox layer is at the same layer with the P+. Okay. If you go back, so see here, here's a P substrate, and then Fox, there's the opening, has a P+ over here. So this is not accurate figure actually. So Fox can go a little bit up as well, and is actually not that low down to the P sub. But if you look at this one, then you look at this one again, it's different. So you can see Fox is here, is on the top of P sub. And how can you embed a P+ in the middle of the Fox? Like this one. Right? How can you grow a P sub up? Right? So this is confusing. So let's take a look at the real microscopic picture and see what's going on, actually. So that's a cross-sectional view of any of the technologies I don't know. This is just from Google. But this is a really nice picture because you're able to see a Fox layer somewhere. You have to zoom in. See, where is actually the Fox layer? So this thing is a Fox. This is also Fox. It was able to opening up a window and dope the diffusion. If you can see, it's labeled as diffusion. So diffusion is just the active, can be N+ or P+, right? So that's a doped material. And it's being protected by the Fox on the top. So the Fox can first protect all these layers to get shorted, and also to reduce the crosstalk between these signal lines. So signals are not easily getting through, or the high frequency AC signals are not just shorting this terminal, since they are super close, like in nanometer level. And here's a gate. You can see Fox is also on the top of the gate as well. And there's a really thin oxide layer underneath the gate as well. It's called gate oxide. You couldn't see here, but it's super thin, right? So the gate is not shorted to the channel. So here's the channel, right? But when you are drawing all these layers, you do not have to draw Fox, because Fox just exists everywhere. Whenever you are drawing something in your homework assignment or in the quiz, you can directly ignore Fox and just draw an insulation layer here. If you do not draw Fox, I won't take points off from the homework assignment. So it's clear for this one. And another thing, last time we mentioned voltage doublers and charge pump. Here's a voltage doubler. And if I have an input signal swing around -0.5 to 0.5, V out will be 1 to 0. All right, that's a conclusion from last time. So I also give you an example like this. And I ask you, it's the same signal, okay? And I ask you that if you probe here, what are you going to get? And why? Why this is different? So definitely, if you have a voltage source like a battery, and connect the battery to a capacitor like this, but there's nothing to close the loop. What's going to happen for this circuit? Yeah, it's a floating wire, and whenever, even though you have a switch, you close the switch instantaneously, it was trying to push. So it's very short period of time, it's trying to dump positive charges into the cap on the left-hand side, right? However, this is disconnected, so nothing can be pushed away. Or you can say there's no place to source electrons to the other side of the plate. So nothing can come back to this plate because it's not grounded. So there's nowhere to source electrons because it's not shorted to a power source. So no source. So there's nothing here. So it's no voltage, nothing. If you have to probe it, it's going to be something around zero, but it's just, you cannot say zero because it's not grounded. It's just unknown. It's a floating wire. But why is this different? Because with this is, whenever the voltage here is higher than here, the diode is getting forward biased. So it has a place to source electrons from where? So whenever this is going high, so all these positive charges are being dumped into the left-hand side of the plate, right? So it's going to push the electrons, it's going to push the positive charges out on the right-hand side away from the plate. To where? So when you dump positive charges to the left-hand side, it's going to push the positive charges to the right direction. Or you can say it's attracting electrons. Or can you do that? Can you really do that? It's being blocked, so the charges has no place to go. But whenever you have this place is more positive than this place, which means the voltage source is a negative voltage, then what's going to happen? So it becomes conductive. It's going to push positive charges to here, right? And then back to here, because here is more negative. Even though this is ground, but actually this is higher voltage than here. So electrons are being sourced from here and being attracted to the other side of the plate. This is how that works. But there's nothing happening here. This is important to understand this because we want to move forward to charge pumps. So we'll understand what's going on over there. Okay. Any questions regarding this? It's important to understand this intuitively, right? Not just the equations. Okay, so if you have a circuit like this, a voltage swing from negative 0.5 to 0.5 can be lifted to 0 to 1. Because at the very beginning, you got a 0.5 volts being charged to the cap like this. And the next time, it is not able to discharge because it's being blocked. So it's going to add up that 0.5 to this, so make the VL becomes 1 volt. If you cannot follow, let's go back to the lecture. I think that was on, should be Wednesday, I guess. Wednesday or Monday, I forgot. Just go back to that lecture and watch the process about how to analyze the charges of the circuit. Okay, so that's a voltage doubler. And as you know, NMOSes are good at passing zeros. So if you want to pass VDD to the other side of the NMOS, it's not possible. Because this, if you give a VG to VDD, and potentially you are able to open up the channel and transfer VDD to this side, so the voltage start increasing. But whenever it reaches VDD minus VTHN, it stops. Because when VS is this voltage, VDD is this voltage, the channel is closed or is off. The channel will be off after reaching this voltage, right? Because VDD is a VG, VS is VDD minus VTHN. So VGS, which is the voltage to turn on or turn off the channel, is VDD minus VTHN, which is VTHN. Cannot be lower. VGS cannot be lower than VTHN in order to keep the channel open. So whenever the voltage here is equal or higher, a little bit higher than this, the channel will be off. So the voltage cannot increase further. So this will be the highest voltage can transfer to the other side of the transistor. So one more question. Is the drain and the source interchangeable? Just in your CMOS C5 technology, in your electric VLSI, are you seeing any difference? There's no difference, right? When you are doing the layout, can you already tell the difference between drain and source? No. So why, if we connect the transistor in this way, why we are saying that this is source, this is drain? Because we're always calculating VGS in this way. But why we not name this guy as S and we calculate VGS in this way? I mean, they are equivalent, they are symmetric. Why we always do that? You know, we just transfer VG to S. What's the trick here? Because if I label this part as VDD and I label this terminal as VDD, it's not making sense to assume this guy to be S, because VDD minus VDD, which is a VGS 0, is lower than VTHN. It's always off. Why are you talking about that, right? So it's not making sense to assume this guy to be S. Since it's symmetric, if we design or define this one to be drain, and we are trying to open this up, this terminal has to be S. I mean, you can assign this to be VDD as well, but in that case, this terminal becomes S. Because we want to have the drain and gate to be at VDD. That making sense? Since you want to pass, you are trying to pass VDD to the other side of the channel. And so you cannot assume this guy to be source right now because it's already off. That making sense? All right. So now I'm trying to pass VDD to the other side of the terminal. I cannot do that, right? And now, already we just talked about the passing the signals to the other side of the channel. So if we have this one pulled up to VDD and VG to VDD as well, are we able to pass signals, or let's say that? So because these two are shorted, that doesn't matter if it's the VDD or something else. Let's just draw the circuit. If I draw something like this, it's the same thing here, right? I can short this one to any voltages, can be VDD, can be something else. Can I pass the signal in that direction? Or not? Can I pass signal in this direction or not? This is important to understand because when I was in graduate school, these questions were not answered in class, and I got confused for a long time. And eventually, I found out that the tricks here. I think it's worth to mention in the class because it takes time for you guys to get clear with all these tricks. If I connect the dial as a, just give you the answer. If I connect the NMOS like this, can I pass the signal from here to here? and why? So if I'm trying to pass signal from here to here, I'm assuming this NMOS is open, which means VGS has to be open. Can you open this channel by shorting here to here? No, because VG equals to VS, so it's lower than VTHN because VGS is 0. Right? Can I pass a signal from here to here? This is called a diode connection. And NMOS, if you connect the NMOS in this way, it's always in saturation. Why? Because VDS is always larger than VGS minus VTHN. Why? Because VDS equals to VGS. VDS equals to VGS, right? Because it's being shorted. So VDS equals to VGS. So definitely VDS is larger than VGS minus something. And what is this? VDS set. So when it's larger than VDS set, it's being operated in the saturation region. So if you short the gate to the drain for the NMOS, it's always being operated in the saturation region, similar to the PMOS. Saturation and the diode as well. Something like this. Okay. Now let's take a look at a circuit using this type of structure. Assume there's a building potential, which is VB, 0.7 volts. And in the digital circuit, we do not have a negative voltage. So all the clocks are oscillating from where to where? 0 to VDD. Is this a voltage doubler? And why? So when you are analyzing a circuit like this, you just want to have an animation in your brain, in your mind, right? Thinking about that. Since the oscillation is fast, it's not steady DC voltage. So the charging and discharging to the cap is always happening. So there's current flowing through in and out from the cap. So whenever the voltage is 0 at the first cycle here, whenever the voltage is 0, here is high, here is 0, you got a voltage potential drop, right? What's going to happen? Will be charged through here, right? So the current will be dumped into the cap. You can just imagine someone is pulling electrons in that direction. But not electrons, positive charges in that direction. So pulling current. So this source is kind of like a vacuum. It's sucking current in that direction. And the current can be sourced from this VDD. It happens in a very short period of time, so it works for this period. So imagine there's a current flow already happening here, right? So what's the voltage here? And because this is 0 volts, right? So the voltage across the plate will be VDD minus VB. And whenever this jumps to VDD, what's happening? If this jumps to VDD, it's a KVL, it's plus minus, plus minus. So what's the voltage here compared to the ground? What is VL compared to ground? 1, 2. What's the voltage overall? And whenever this goes back to 0 again, so this becomes 0 again, what's the voltage here? 0 adding to this guy is still, so the voltage output is going to swing like this. And this voltage will be 2 VDD minus VB. And then what you want to do is rectify it to filter it so you can get a pretty much a DC signal which is higher. So that's why you can double the voltage. It's not actually doubling because it's not IDUI diode. But however, you can definitely boost the voltage to something. Since originally I have VDD, but now you have 2 VDD minus VB as a DC voltage. It can be a little bit lower than that, but actually it's already boosted. If we replace this diode using our diode connected NMOS, then we can form a charge pump. So that's a circuit for the charge pump. Here's a diode, here's another diode, that's the rectifier, that's the voltage doubler. All right. You can see the exactly same circuit from Dr. Baker's textbook. It's in a special IC design chapter. And we can further boost the voltage by connecting more charge pumps in series. And the circuit looks like this. It's called the Dixon's Dixon charge pump. see how this works. Can further boost the voltage. So clock is definitely, there's no negative voltage for clocks, right? Again. So this is inverted clock. Just inverted using the inverter. So whenever this is 0, what's happening for this cap? A pull current, it just pull charges from this side of the plate, which will pull charges from VDD to here. So it's going to charge up the cap. So what's the voltage here at the first cycle, after the first cycle? VDD minus VTHN, right? Because it's a diode. Whenever it's higher than VDD minus VTHN, the channel is off. So cannot further being boosted to VDD. So cannot directly go up to VDD because there's a threshold voltage drop across this NMOS. And whenever this is VDD, it's just adding VDD to it. Right? So the voltage here at A is going to swing from 2 VDD minus VTHN and VDD minus VTHN. And this voltage will be transferred to here whenever this is low. So whenever this clock is pulling charges from this side of the cap, and it's gonna charge up the other side of the cap from here using voltage. Because whenever this is low, this is high. Whenever this is high, this is 2 VDD minus VTHN. So the 2 VDD minus VTHN will be transferred to here, plus another VTHN drop. So that will be 2 VDD minus 2 VTHN as the highest. Oh, no, as the lowest. Because whenever this is low, it's pulling the charges from here to here. Right? So this is the lowest. And whenever this is high, it's just adding another VDD to here. So that will be 3 VDD minus 2 VTHN. This is lowest, this is highest. That making sense? Hopefully. What about terminal C? Whenever this is low, it's pulling. Whenever this is low, this is high, right? So it's pulling the highest, which is this one to here, but further dropped by another VTH, N. So it's literally this guy minus another VTH will be the lowest. And this guy plus VDD will be the highest. I'm making this correct. Oh, 4, yeah, 4. 4 minus 3 and 3 minus 3, yeah, that's right. I can compare that the voltage is being lifted for every single step after this, right? So I understand this is important, and we're going to cover the sample and hold circuit on Monday. Lecture on Monday, right? Yeah. Let's do the quiz today. Start with the quiz.